Okay, the title of my talk is Dynamic Ferroelectricity of Trojan Electrons on Parallel Kagome Lattices. Let me make the introduction. What is the Trojan wave packet? And you can call it ultimate limit of the photomechanics. And Trojan wave packet is basically the single atom electric motor powered by the circular polarized electromagnetic field. So you put hydrogen atom in the wave with the circular polarization. And in certain conditions, you are obtaining the motion of the electron with the phase of the rotation of the electric field vector. In the solid state, of course, the light, the matter, light is diffused, and you get only the essential region of the position of the electron, and it's the rotor of this electric motor, and the stator is the proton, and the powering field is simply the circularly polarized field which is rotating in the plane of the circular polarization. And the state, this state was discovered by me, by my informal thesis supervisor Ivo Biański-Birula, who got recently the Wigner Medal for also for discovering Trojan wave packets, among other contributions to the quantum mechanics, and with Joe Ebeli, who was my formal thesis supervisor at the University of Rochester in 90s. And again, this is the solid on the electron probability density in the hydrogen atom, which is orbiting the proton when you add the circularly polarized field and they simply irradiate the atom with the circularly polarized field under certain conditions. And why we call them Trojan wave packets? Because the problem mathematically maps on old astronomical problem of Trojan asteroids. Trojan asteroids are basically big stones orbiting the sun in phase with Jupiter, and they are located at so-called Lagrange equilibrium points L1 and 4 and L5 in phase with Jupiter, and the conditions, the time-dependent gravitational field is creating at these points is identical to the conditions of the created by the circularly polarized field driving the Trojan wave packet. Okay, so and Arisen described formula relating simply by matching the parameters, relating the gravitational constant to the parameters of the quantum electrodynamics, which is crossed Planck constant, speed of light, mass of the electron, and the fine structure constant. And this explains why the Trojan asteroids are so big with respect to the Trojan wave packet, because the power of the pi structure constant here is 21. So you see, and this term, of course, has the same dimension than the gravitational constant. You can call it a strong gravitational constant. And I matched the coefficient in the sense of matching the Rydberg spectrum to the transitions first observed when no one knew Schrödinger equation. And I found simply that if you can call it quantum number, the quantum number of routing the number 2 is 38. For if you consider the spectrum, you put n here, the 38 is matching perfectly the gravitational and non-gravitational value of the non-gravitational constant. Okay. The simplest theory of the Trojan wave packet is obtained by going to the rotating frame and solving the classical equilibrium point when you have classical equilibrium point, the rotating frame, you can expand the Coulomb potential up to second order around it, and you will find out that the Trojan package is described by the two coupled harmonic oscillators, and they are coupled by the rotation. This is omega LZ basically. XPY minus YPX is LZ, and you allow this harmonic oscillator to have negative curvature, which is the hill in one direction and the minimum in the second, or if you generally you can consider this Hamiltonian when there is both B and A and B is negative. There you have two-dimensional maximum, and of course the red zones are unstable motions and the blue zones are stable, and the thin black line is the constraint, which is obtained simply by the equation of forces from the electric field of the rotating wave and from the Coulomb force from the proton. Okay, and you see the Trojan wave packet is here in this region when the A is positive and the B is negative or opposite, uh, and this means that it is bound by the rotating saddle point. It's not in the minimum, but in the rotating saddle point. You can also, if you go back in time, you can also map the Trojan wave packet on the panning trap. The difference is that the panning trap is normal. Panning trap is cylindrical. It has a cross-section circle, but this is elliptical panning trap. Elliptical panning trap you can see basically in most of cars. It is a car muffler, okay, by shape. Mufflers are very rare, which are cylindrical, but most of mufflers are elliptical, and the reason is of course the space under the car, and you will find out that this panning trap is not only elliptical, but it is operating in abnormal mode. That the field is stabilizing, the field is still stabilizing. The native electrostatic potential here is this term with negative sign plus the parameters of the Coulomb potential. But the native potential which is stabilized is also maximum, but it is elliptical maximum. Why the trap is elliptical? But if you do the stabilization, that you will find out that the stabilization is to a saddle point, which has still this term, which is for normal cylindrical panning trap, and this term for normal cylindrical trap is doing almost nothing mathematically. It is only rotating the trajectories. When you solve for trajectories in the harmonic oscillator, then you simply rotate them by the geometric rotation to obtain the ones in the lab frame. Okay, and but here this term is doing this term. The original panning trap resembles behavior of the umbrella on strong wind. Okay, you know that if you take umbrella, it will flip the curvature. Okay, and on strong wind, and this what is doing the normal trap, and this term is only doing the geometric transformation of soft trajectories. But in case of the elliptical panning trap working in this mode, the elliptical maximum is stabilized to saddle point. This term is essential because it is stabilizing. This term is stabilizing. If you take the saddle point without this point, the particle will fall down the valley. In one direction, the potential goes down indefinitely. Okay, and you can also reconstruct the original stability diagram, which we derived by the canonical transformation. You can do it either classical canonical transformation or simply demanding that the eigenfunctions of this Hamiltonian are normalizable. Okay, and you will find out that you can obtain this qualitatively. You can obtain this diagram also intuitively. For example, a lot of cases like you consider the potential which has a very strong positive curvature in one direction and slightly a negative curvature in the other, which would correspond in the simplest model to the rain gutter from the house, which is slightly folded. Okay, someone folded the rain gutter slightly upside down and put it horizontally. That if you put charge ball there, that you know that the Earth magnetic field is so weak that it will not cause, and it will cause almost nothing on charge ball. It will still fall down along the water flow direction. Okay, the water confining direction, it will be oscillatory, but in the water flow direction, no matter what you do, if it's only Earth magnetic field, will not stabilize. So you can conclude a lot in the seeing this intuitive picture that this is the you add and subtract the diamagnetic term, the artificial diamagnetic term corresponding to the rotation. You consider the action of the magnetic field on the combined potential, which is this black term, and this is the red term with the minus sign. You a lot of can predict, of course, intuitively, and you qualitatively get almost the same stability diagram. You will not get the zones precisely. You will not get the steel fighter shape of this. This looks like flying wing airplanes. Okay, and you will not get the curvature, but you will get cut. But qualitatively, you will obtain. Not calculating anything, simply imagining what happens if magnetic field is acting on various potentials. You will get qualitatively this picture, and also you can look at the dynamically in the rotating frame, averaging the saddle point rotation. If you look at the saddle point, it has two planes. One plane is cutting to normal parabola, and the second plane in this direction is cutting to parabola upside down. So all these parabolas are drawing, one is drawing potential two-dimensional minimum, a second is drawing potential maximum. And you can simply intuitively demand that if the curvature this curvature is dominating over this, simply a plus b is greater than 0, then you can expect stable motions in the lab frame. And this is reflected here exactly, that this is the line a equal minus b, and this triangle is above. This triangle is fulfilling this standard. So you can get at least the half plane without further consideration. You can go from this dynamical stroboscopic image of rotating saddle. Okay, so since the theory was facing critics that it is maybe it's not too simple, but it is not handling properly the numerical simulations around the equilibrium point, which are exhibiting chaos. We constructed of course we know that the classical and quantum mechanics for very light particles is completely different, because if you take the Bohm approach to quantum mechanics, the Bohm hydrodynamical approach to quantum mechanics, you rewrite the Schrödinger equation in terms of the equation of the massful fluid. You will find out that each particle of this fluid is not only under influence of the external potential, classical potential, but it is also under influence of the potential of the quantum potential, which is derived from the density itself. So it's self-consistent. Okay, so and you know that all the ground states are in the equilibrium. That exactly for ground states, the force due to the classical potential is balanced by the force of the quantum potentials, and that is why the ground states are not collapsing to minus infinity, for example, for the hydrogen atom, for the mathematical hydrogen atom. And therefore, we constructed a more complicated quantum theory, which is solving the Hamiltonian of the problem. This is electric field, which is the problem of the crossed electric and the magnetic field, which the magnetic field is not full because the diamagnetic term, which is quadratic, is dropped. We solve this Hamiltonian eigenvalue problem of this Hamiltonian in the basis of the hydrogen, simply in the basis of the hydrogen eigenstates, the same as you handle the Stark effect or the Zeeman effect with the perturbation calculus. And I have to underline that this is not the perturbation calculus. This is above perturbation, and we obtained that the Trojan wave packet is simply the topologically simplest eigenstate of the quantum pendulum with the negative mass. So let me underline that the quantum particle with the negative mass put on the hill is not the quantum particle on the hill with normal positive mass, because with normal positive mass, this problem has no distinct spectrum. However, if the particle has negative mass, for example, the quadratic hill is the harmonic oscillator upside down. So the energies are still going to, the quantum energies are going to minus infinity, but they are distinct. There is no collapse. So, but if there is no field connecting, there is no interaction connecting the levels, such particle can stay on the top indefinitely. However, the particle with positive mass, since the spectrum is continuous, we have decay rate and it fall down. Okay, so the Trojan wave packet corresponds to the quantum pendulum state, which is upside down, however, with negative mass, and therefore it is the Gaussian and this topologically simplest state. There is no nodes, because you know that if the mass of the particle is positive, then the higher energy, the more excited it is in the sense of nodal properties, it has more nodes. The Hermite polynomials and the Mathieu functions have this property for normal. So you see that here the particle has the highest energy, but topologically no nodes. Okay, so this is what is so interesting about it, and I think in some sense the balloon, the helium balloon, the hydrogen balloon is in the Earth. Gravity is reflecting this behavior because the equilibrium is upside down. Okay, and so you can also look at the Trojan wave packet as the eigenstate of the one-dimensional solid. You will see it clearly as if you if you consider the tuning between the energy levels of the hydrogen, because Trojan wave packet is centered in the sense of the theory I mentioned with the hydrogen basis is spanned basically around the resonant level. The spacing strictly in this theory, the omega of the circularly polarized field is 1 over cubic power of the central quantum number. But if you consider the tuning from this condition, you will get the linear term in d over dx, and therefore you will get the Trojan wave packets as the Bloch function of one-dimensional solid with the tuning. Okay, you can and the periodic potential is the cosine potential. You have a lot of models. You have Koenig-Penney models with a Koenig-Penney model with simply the well potential, but you can consider also solid with cosine potential, and then the eigenfunctions are Mathieu functions. and you will get the Trojan wave packet as the block function. Okay, so of one-dimensional solids. So this is how the Trojan wave packet looks volumetrically. It looks like some fruit. This is the quarter of it. I cut two perpendicular planes are cutting into half, so it is quarter of it, and it is simply in the limit of the quantum numbers going to infinity, the central quantum number going to infinity. It is becoming point relatively to the radius of the orbital motion. Okay, so in some sense it is the point classical correspondence of the quantum mechanics of the hydrogen atom in CP field, except that this is only in some sense, because the packet in absolute distance values is becoming still bigger and bigger. It only looks smaller and smaller with respect to the orbit, but this is still not completely the classical particle, no matter how quantum number high is. Okay. So now let me go to the ferroelectricity. What is ferroelectricity? If you know a little the condensed matter theory, that you know the ferromagnetism, that all the magnetic moment of the inside the medium, no matter what the origin is, are polarized in one direction, and therefore the probe is becoming the permanent magnet. Okay, and ferroelectricity is something identical, but with the electric dipole moments. Okay, and so there is a non-vanishing polarization inside the medium, but there is no external electric field applied at all. So it is simply remembering that something polarized it, and it stays like that. Okay, so we constructed in the beginning of 2000 years, we constructed something which we called Rutherford atom in quantum theory, because it corresponds basically to the early models of atoms. Okay, and Rutherford model assumed the point like electron, and you can also consider it in some sense the Bohr atom, but it requires two electrons. So for hydrogen alone there is no. But we call it Rutherford atom model, Rutherford atom in quantum theory. And how was constructed, we put one electron in so-called elliptical state. And what is elliptical state? It is basically the state corresponding to the elliptical. If you know the Kepler problem, the solutions are in circle. They are conic curves, and they are either a hyperbola or ellipse or circle, depending on the energy. And in this case, the elliptical state corresponds to is the quantum correspondent of the elliptical orbit, and it is constructed simply by the state within one quantum number energy manifold, which has different quantum numbers L and M, and they are equal. They superpose from the eigenstates which have equal L and M, or in modulus, of course, because M can be minus also negative, and depending how you define, and they are localized around the ellipse, and they are solution. So basically, either you can look, there are solutions of the Schrödinger equation of the Hamiltonian of the crossed electric weak magnetic, and if you look closer at the magnetic field, that really the approximation that you neglect the quadratic term cannot be made because but you do that sometimes, that you only consider it omega LZ, that omega is twice the cyclotron frequency, and uh, you can either look at this Hamiltonian as the weak magnetic field crossed to electric field, or you can look at this Hamiltonian as this is the A is the AX is the X component of the Runge length vector, and this is LZ component of the angular momentum. So this is either the Hamiltonian of the hydrogen atom in the crossed electric and magnetic field, or the Hamiltonian in rotating frame of the hydrogen atom in circularly polarized electromagnetic field, but not in resonant conditions. Okay, that this is very slow. That the rotation of the electric field is slow, and what is happening basically, that the basic mechanism that this is the eigenstate is that if you put such state, if you put such state in the external static electric field, it will along the longer ellipse axis. When it is localized around the ellipse, then you can find the axis of this ellipse, and if you put the electric field on this axis, it will start to avoid it, and it will precess. And now if you follow this electric field adiabatically, then you will maintain this elliptical state indefinitely. So it will simply follow the electric field. Okay, if you properly tune the omega to the electric field strength, because the state is eigenstate of this problem. Okay, and despite that, this is also eigenstate of the hydrogen with the fixed energy. Okay, so energy, so all states which are spent within manifold are eigenstates of the Hamiltonian. Okay, and the states within manifolds are eigenstates of different operators, and so but here it is eigenstate of the Hamiltonian with the external electric field, and it has and we use this property to construct the dynamically polarized single atom first. When you replace the external electric field by the field of the other electron, for example, precisely in the Trojan wave packet, okay, then you will find out that Trojan wave packet is generating field which is causing precession of this state. But this state is generating the dipole moment in reverse, which is maintaining the Trojan wave packet. So self-consistently, such atom will have a permanent dipole moment. Permanent. There's simply symmetry breaking. It has permanent dipole moment, and this dipole moment is eternally rotating. Okay, and this is the quantum simulations, two-dimensional simulations of the outer electron in the Trojan wave packet state, and this shows up that the inner state is following. The inner state shape resembles some finger ring as you look, and it is following the Trojan wave packet motion. And of course, since if you neglect the radiation effects, the spontaneous emission and simply radiation, then we find out that this state is similar to the Meissner effect. It is persistent current of the outer electron which can indefinitely move. Okay, so now here is the movie of two electrons interacting with each other. The basic nature is the same. That one electron has influence on the other. Not only the distances between them is determined by this is two electrons in the harmonic oscillator, simply solved within Hartley approximation. So you see that The influence of the interaction is that they will repeat their motion in shape. So one electron is causing the other changing shape, and in reverse, and as a result, self-consistent result, they are repeating their own shape because the problem is symmetric with respect to electrons. Okay, so this shows the influence of the Coulomb interaction on the confinement of the packet. Okay, so now we ask the question: can we go beyond the Rutherford atom that there are only two electrons, and can we simply create a system when one Trojan wave packet is supporting the other? Because if the Trojan wave packet is the source of the giant dipole moment, it like the elliptical state in the former case, it may support the other. And we ask, can we put such atoms on on regular lattices so that they support each other self-consistently? And we found out that we used the Bethe-Pyers Weiss approximation from the theory of ferromagnetism, when you consider that the single atom is simply in the in the theory of ferromagnetism, you use the exchange interaction ordering. The difference is that in the theory, you know that the magnetic interactions between magnetic dipoles are too weak to cause ferromagnetism with the measurable Curie temperatures, but here they are precisely these interactions. And we considered the influence of the nearest neighbors on the generating effectively the CP field in the vertex of the in which the central atom is placed, and you will find out that I call this equation Hartree Bethe-Pyers Weiss equations. These are coupled Hartree equations, and you get basically the on honeycomb lattice you get the ferroelectric order, and when both the densities are in phase, okay, and antiferroelectric when the nearest neighbors, when the density between the central atom and the nearest neighbors is in pi phase, okay, in opposite phase, opposite polarization. So you can, if you do the dipole approximation from classical electrodynamics, for example, from the classic by Jackson, then you will find out that indeed the field generated by the nearest neighbors is circularly polarized. It is, for example, for honeycomb lattice for three neighbors, it is 3 second times the dipole moment divided by the cube of the lattice constant, and therefore the strength of the local field is approximately 3 times the radius of the orbital motion of the Trojan wave packet divided by twice the cube of the lattice constant. Okay, and the basic condition for existence of such matter is, of course, that this local field is not exceeding the critical field from a theory of the Trojan wave packets. In the theory of the original Trojan wave packets in CP field, it appears that the stability of motion is destroyed when the field strength is too strong, and this is the scaled field strength, the strength of the electric field at the ratio between strength of the electric field and the Coulomb field at the point of orbit. And if you exceed the approximately there is a analytical expression for it, but if you exceed 0.11 approximately, then you will get the unstable motion, and the packet basically will be ionized. Now, okay, you can now look at also at the problem with the higher resolution at three atoms with the classical atoms with electrons moving on circles, and you can ask what is the field seen by the central atom in the vertex of this lattice, and you will find out that the higher the ratio, the smaller the ratio between the radius of the orbital motion and the lattice constant, the better approximation, the better the field is resembling the circular polarization. Okay, so in the ultimate limit, of course, these are simply dipoles. Okay, because dipole has the radius has zero, but the radius times charge is going to charge is going then to infinity, and but the ratio the product r zero times the charge is finite, the finite dipole moment. So the high ratios corresponds to the perfect, almost perfect dipole moments rotating, but the low ratios, you get some funny curves which resemble Lissajous curves, which you can obtain by the old analog oscilloscope by simply putting the horizontal deflection voltage and time dependent, and the vertical deflection voltage to harmonic and with different frequencies. So, but here some funny shapes, and for 1/10, for example, the triangle is already approaching the circle because it has smooth edges, and for 1/100 already there is an egg which is resembling the circle, and for 1/1000 it's already almost perfect circle. So this corresponds to some light, neither circularly polarized or linearly polarized, but the vector, the hodograph of the vector, the end of the vector is following Lissajous-like curve. Okay, for low ratios, but nevertheless, it says that in all these motions there is as you see, it's a closed trajectory, and it is periodic, so there is a strong circular component, so it can still maintain the packet, and this is basically on honeycomb lattice you obtain ferroelectric, anti-ferroelectric order when the red sublattice and the blue sublattice have Trojan wave packets with the same absolute value of the dipole moment, but they are in anti-phase, simply phase shifted in when one is polarized in this direction, the blue is in opposite to self-sustain, and for native ferroelectric order, when they all are in the same polarization, that they are in so-called anti-Trojan wave packet state. And if I mentioned that the Trojan wave packet is within nonlinear theories, the quantum pendulum state, of course, quantum pendulum state has two significant states. And one corresponds to so-called separatrix in the spectrum, and you see that there is a the higher density of states which separates the rotational motions from the oscillatory motions, and anti-Trojan wave packet state corresponds to the pendulum upside down, true pendulum with positive mass upside down. If you consider the topological property of nodes, but however, here, since the mass of the pendulum is negative, it corresponds to the state of the lower energy. Okay, so true pendulum, of course, upside down has higher energy than pendulum in equilibrium, but if the mass is negative, it's all reverted. The nodal properties becoming more and more complicated with de-excitation, not excitation, and the other state, the state opposite to Trojan wave packet in this sense is the anti-Trojan wave packet, and you can get only On honeycomb lattice, you can get only native ferroelectric order with anti-Trojan wave packets. So these are the two-dimensional quantum simulations, Hartree simulations of the one electrons on and here since they are in an absolute value are the same. I only plot one electron because the other is simply in antiphase and is the same. So if this one is here, the other is here. Okay, on other sublattice and with an antiferromagnetic order, and after some time they are becoming slightly worse, but you can reach the conditions that they are perfect. And uh, you can also obtain anti-symmetric anti-ferroelectricity when the values of the dipole moments are different on different sublattices in absolute value, and I call it anti-polarization asymmetry displacement field. And you can also you have to solve the equation that one sublattice atoms on sublattice one sublattice are subjected to nearest neighbors from the atoms on the second, and you have two system of nonlinear equations when the first dipole depends on the local field generated by one sublattice, second dipole on the local field by the second one. Okay, and here is the effective nonlinear equation. Uh, These are special Bessel functions I1 and special Bessel functions I0. Okay, and you can get central approximations using our nonlinear theory. You can get the analytical expression for the polarization of the dipole moment with respect to the scaled electric field, and these are the curves when the ratio between dipole moment and the distance the orbital radius is plotted for various quantum numbers. So you see that for quantum numbers around 100, the atoms become very sensitive, and they resemble the curves resemble saturation curves of the electronic transistors. You know that if you put the base current sufficiently high, there is no much influence of the emitter collector current in the transistor on the voltage applied there. Okay, and this exhibits similar characteristics. And also you see that this is value 1. So in the limit of high quantum numbers, the dipole becomes basically the radius, the value of the dipole becomes the radius, putting the electric charge 1 becomes the value of the radius of the orbital motion. And the more quantum, the more deviation. For an equal 2 is completely deviated from this classical picture, but for an equal 100, it's almost the classical picture of the point-like charge moving on the circular orbit. Okay, so on the honeycomb phase center lattice, you already get two-color asymmetric anti-ferroelectric order with Trojan wave packets. The native ferroelectricity is anti, and you also get the also, like with normal honeycomb, you get ferroelectric order with anti-Trojan wave packets. Okay, only all in the same states, supporting each other because each state is surrounded by the same nearest neighbors. Okay, and you get also more complicated orders. I call it linear antiferroelectric orders when the atoms are on lines, angled lines, okay, red lines and blue lines. You also get self-consistent equation, also three-color ferroelectric order when various atoms are in different in Trojan wave packet state with different absolute value of the dipole moment. And also the self-consistency is obtained in the better Pires-Weiss approximation that the one atom is subjected to the CP field of the three neighbors. Okay. So this is, for example, numerical simulations on two different sublattices for phase center lattice in the here in the asymmetric antiferroelectric order. This is the D1 sublattice, and the second is D2 sublattice also. So you see that the confinement of the packets on different sublattices is different. There is stronger, and here is weaker. Okay. So let me now go to Kagome lattice itself. It is a more complicated lattice, and you will notice that if you try to use Trojan wave packets and the native antiferroelectric order, that it is not possible, because you will find out that the basic cell, the beta Pires-Weiss cell, is self-contradictory. If you take this orientation, that this is the dipole in this direction, that is opposite to support it, then you will find out that this on this cell, the direction is here, direction is here. So the conditions for this cell are different. So you cannot get the native. So I call it that the beta Pires-Weiss nearest neighbors are not augmented, because you get self-contradictory conditions for these cells. Okay, and the second difference is that if the basic cell, basic beta Pires-Weiss cell is not the regular polygon, this is rectangle or square, then you will get that the field generated by the nearest neighbors is no longer circularly polarized, but it is elliptical. And you know that each elliptically polarized wave, as well as in extreme, the linearly polarized, okay, so maximum eccentricity, is a superposition of two counter-rotating CP fields. So what you basically do, you decompose the elliptically polarized field generated by nearest neighbors into the component which is co-rotating with the wave packet and counter-rotating, and you neglect the counter-rotating component, what I called the real space rotating wave approximation, in analogy to the normal quantum optics rotating wave approximation, when you considering, for example, interaction on two-level atom with the external field, you neglect in calculations the terms which have phases which are ultra fast rotating, comparing to the resonant phases. That omega is basically approximately the spacing between levels, and there are other terms showing up that omega is plus the spacing is twice omega approximately. You neglect these terms. Okay, and here you neglect simply the component of the elliptical field, which is counter-rotating with respect to the packet which this field is supporting. Okay, so there are two differences, that you cannot get native antiferroelectric order, and you cannot also consider the field as CP field. And here you also have photographs for the case of this lattice, that you get the ellipses in the limit of a very large ratio of the lattice constant, which is each of the basic equilateral triangle of the Kagome lattice, and if this ratio goes to zero, that you get perfect ellipses, and if this is small, then you get also some Lissajous-like curves, very interesting. For example, here, of course, they all have elliptical component if they are closed, if they are periodic curves, but and in the limit they are approaching ellipses, so they have component which can support, but they have also very high harmonics. Okay, and they don't correspond neither to linearly polarized or elliptic or polarized light. Also, this is some Lissajous polarized light, and the in the limit of the if this ratio goes to zero, you get perfect dipoles, and the field is the ratio between the x component and the y component in this limit. You can see it here that this ratio of this axis it's indeed about 3, and it is exactly 3 if you calculate. One has this is ex, this is ui, and 9 to 3 is 3. So this is the electric field in the perfect limit of the pure dipoles, causing the influencing the nearest neighbor atom. Okay, and also, you can get the index in case of Trojan wave packets. Let me again recall that these are all two-dimensional lattices. That you get anti-symmetric linear anti-ferroelectric order. So the neighboring atoms, blue atoms and the red atoms, are in the anti-phase state, and you get the native ferroelectric order, which is all atoms are in not Trojan but anti-Trojan state, which is the state of the lower energy, but corresponding to pendulum with positive mass, which is upside down, and but negative mass it is upside down, but topologically it is complicated, but it has lower, it is upside down, but has lower energy. So it is there is anomaly because of negative mass. So this is the native ferroelectric order is from anti-Trojan wave packets, and also you can get a three-color ferroelectric order when the with Trojan wave packets, when the absolute values of the dipole moments are of three kinds. And for example, here is magnification, that the one when it's a one-time shot, when the blue atoms have large dipole moment up, the green and the red atom have different and in opposite direction. Okay, so these are now the question raises: can we obtain on these lattices the native ferroelectric order when all atoms are in phase in Trojan wave packet state? We want all atoms in phase in Trojan wave packet state, and the native ferroelectric order. And the question is yes, but we have to consider, go to 3 dimensions and consider the parallel layers of these Kagome lattices, and what you will find out that the neighboring the neighborhood of the parallel planes is supporting the Trojan wave packets in phase, and you can calculate actually the having this expression for the electric field. Of course, you can find out what are the components, what are the components of the co-rotating and the counter-rotating, and the co-rotating. You find out that co-rotating has strength 6 in these units, and counter-rotating has 3. And if you now want that actually the co-rotating in this sense is if they are only phase, it is preventing Trojan wave packets. So to balance by the interlayer interaction, so you will find that way. If you want that this pro order field is larger than the preventing field within the layer, you will get the pro order field is minus 2 d over b to cube to power 3 when the b is the interlayer distance. You will get this interesting, beautiful number 1/3 to 1/3, and the distance between planes to the lattice constant of the Kagome lattice must be less than 1/3 to 1/3, and it's approximately 0.69336. If you exceed that, you can get the native ferroelectric order when all atoms are in Trojan state, and they are all moving in phase. So the net polarization is non-zero on the macroscopic scale. Okay. Let me summarize now that in 1993 we discovered Trojan wave packets, the stable shape invariant solitons of the electron probability density orbiting the hydrogen nucleus in phase with the rotation of the circularly polarized CP field, electric field vector in the dipole approximation. In around 2003, we have realized that such packets can be also supported by the rotating dipole moment in the closed radiation zone generated approximately CP field, what allowed us to construct a dynamically ferroelectric helium atom, which is also the true quantum realization of so-called Rutherford atom, where the Trojan and the Absidali precessing dipoles are rotating in phase and stably polarizing each other. The question therefore raised, can Trojan wave packets alone as the sources of the rotating giant dipole moments have consistently support each other on lattices and therefore maintain the persistent rotating polarization without the external CP field added? And we have discovered several dynamically rotating ferroelectric orders in the regular 2D lattice. Let me come out here that again, I want to underline that if you know the early theories of the ferromagnetism, there were attempts that the people were thinking first that maybe the magnetic interactions itself are causing ordering, and because they didn't know anything about spin and statistics, and they didn't know about exchange and order interactions for many body fermion systems, and the Heisenberg Hamiltonians, and they were thinking that maybe this is the like you take two magnets which are rotating. You put them closed, and you see that they will order, and they are thinking that, but here it is precisely this is precisely as early theories of the ferromagnetism, except that these are electric dipole moments, not the magnetic dipole moments, and the true dipole moments are interacting to self-sustain the polarization. Okay, so let me continue here that as well as on two-dimensional Kagome lattices in the physical space rotating wave approximation applied to the elliptical polarization when the electric polarization electric vector component counter-rotating with respect to the wave packet motion. Again, the wave packet is moving on a circle, it has one angular momentum, and the field has two components. One is co-rotating, second counter-rotating with the same frequency absolute value, and the counter-rotating motion is neglected. And we find that the native ferroelectric order with all in phase Trojan effect is possible in two-dimensional Trojan matter consisting of the parallel Kagome lattices upon crossing the critical interlayer distance parameter, and they can be confirmed in the Hartree-Fock 3D grid simulations in the Hartree limit, as well as within the stationary now recently developed new time-dependent quantum diffusion Monte Carlo method. I recently developed the time-dependent quantum Monte Carlo diffusion method when the wave function itself is represented by two kind of walkers because imaginary and real, and by two color walkers, and these walkers are interacting. They exhibit diffusion and annihilation and creation that you can emulate the arbitrary number of electrons, statistical probing arbitrarily a number of electrons sharing an equation. Okay, let me stop now. Thank you.